Okay, welcome to CE 528. And in the last class, we were talking about the idea of demand curve. And we also learned how we get to the demand curve. We learned about cross elasticity. We learned about elasticity. The idea of elasticity is that what happens to the quantity demanded if the price changes for that same commodity. And then cross elasticity was what happens to another quantity, a competing good possibly. And then we talked about how demand curve slopes downward and all that. And then we always assume the utility maximizing behavior and things like that. So this was essentially what this was the basics of demand modeling or demand. Like, how do you model demand? How do you characterize demand as a function of price? And this is something that you would find in your traditional economics textbooks. Now, what we want to do is we want to extend that analysis a little bit further into the transportation demand theory. And so we want to apply all the knowledge that we've just gained to the idea of the transportation demand. So transportation demand is in fact a special case. And it's regarded as a derived demand because the demand for transport doesn't exist on its own, but because of place utility obtained by moving people or goods to other locations. And we mentioned that there are some exceptions to this. That sometimes you do travel on the scenic route for the sake of traveling, but for the most part, for the most sense, the demand that we consider is in fact what we call a derived demand. And then that means that, so for example, people who are traveling on California Boulevard at any given day, at any given time, they're probably not, let's say if they're traveling northbound on California Boulevard near campus, they're not traveling northbound on California because that's what they want to do. What they're doing is they're trying to get to Cal Poly, for example, right? So Cal Poly is that place utility that they're trying to achieve. So that's how you have to look at the derived demand. And there are some interesting implications of this. Like, where do we, so that derived demand idea is what makes transportation so very linked to the land use issues, right? I mean, we have to think about transportation and land use almost as one thing. You cannot think of transportation and land use as two different things. I think we haven't, because we have looked at building housing so far from city centers, that has led to a lot of the traffic woes that we encounter, really, and that really is the problem. So yeah, if we can think about transportation and land use sort of together, because transportation demand is in fact a derived demand, it's based on the place utility. So you have to think about that place utility that's often characterized as land use, right? So you have to think about those things together. So how do we actually express this demand? We can express it in terms of total trips per person hour per day or per hour. You could do it per hour, per day, and that's demand. We do some of that, if you recall from CE 321, when we are doing traffic assignment. That's sort of the thing that we do. We try to look at total trips per person per day or per hour. We can look at trips per time period from A to B by a given mode. And then also we can look at not just the passenger demand, but we can look at also the goods shipping demand, which will make the last point, which is tons per mile, tons per time period, tons per day, or tons per month shipped from point A to point B by a given mode. Then price will be just usual average perceived cost. And this is interesting because we talk about perceived cost here. So I want to highlight that a little bit, that the idea is that we are talking about perceived cost here. Because if you think about, for example, the mode of driving, when we drive, and I don't do it either. So when we drive, we don't actually take into account all the costs that we may be incurring. So that's why the word perceived cost is somewhat critical here. Because when you're taking transit and you have to pay out of pocket, then that becomes your perceived cost, and your decisions, your demand for travel is dependent on that perceived cost and not really necessarily the actual cost. And that's the idea why. Can you relate this concept with how you all use slow transit, San Luis Obispo Transit? How you guys access slow transit? And what is your perceived cost for taking slow transit? So some interesting responses there in terms of travel time. Yes, travel time that you're experiencing is a perceived cost. And then plus the fare that you pay, which is zero. So your perceived cost of traveling in terms of dollar amounts is zero, because you can just swipe your Cal Poly ID and get on any slow transit bus at any time. So your perceived cost is zero. And you know, right, if everybody had to pay on average what Cal Poly pays to slow transit to have this service attached to your Cal Poly ID, you know, they have every year they have this big negotiation between Cal Poly and the city of slow transit in terms of what Cal Poly is going to pay upfront for the students to be able to use that service for free, or for free of cost. What do you think would happen if Cal Poly and San Luis Obispo Transit could not reach an agreement? But let's say like they didn't charge you the full fare, but they just charge you on average. Let's say Cal Poly pays them $1 million. I should remember this off the top of my head, but I don't. But let's just say, for the sake of example, that there are 500,000 trips that are being made using slow transit. Okay, so 500,000 trips and $2 million is what Cal Poly pays to slow transit. And I'm just making up numbers here to keep them easy and simple. If that's the case, think about what would happen to the demand if everybody had to pay the per trip cost that comes out of those numbers, instead of Cal Poly paying upfront $2 million at the beginning of the year or whenever. If every student had to pay that money, even assuming there was no friction in terms of paying, so you didn't have to look for coins, you could still pay the same way just by swiping your card. Do you think the demand will change in that scenario? And I'll write down the numbers in the chat and then you can respond. So there's some interesting questions. So what we said was that instead of Cal Poly paying $2 million for 500 trips that our students make to use the slow transit buses with their free Cal Poly ID trip, what if that system was replaced by the equivalent per trip charge that you had to pay? So I think a very logical answer is that the demand will decrease. I think that's almost certainly will happen. I think one of the students responded that, okay, I would need to know what that equivalent cost is. And then that's a good point too, because you would want to know that equivalent cost. Right now, you don't care about that equivalent cost as much because that perceived cost is essentially zero. But if you had to pay out of pocket, you would want to know what that cost is. And that gives you a hint as to what it might do. And if it's like 20 cents or 25 cents, maybe you'll say, okay, yeah, no worries, I don't care. I'll just go ahead and pay it. But then, there might be some people who might switch to alternate modes because of that charge. So this is going to be very interesting. But you're right. So the demand will go down because all of these demand is based on what we call the perceived cost, not the actual cost. Any questions about this? Oh, and one more thing, then what we can do is like, you can also, I know somebody mentioned that they're like, the one part of the perceived cost of taking transit is the bus. I mean, it's the actual, travel time that it takes to walk to the bus stop and then go. When I used to live in a Atascadero, if you were coming at certain time on campus, it was almost better for me to take the bus so that I get off right at the library and just walk up than to bring my car to campus where I had to park like almost 3/4 of a mile away to get to my class or wherever I was going then. So yes, but time is money is that absolutely critical. You have to look for. So when you say perceived cost or price, it could be not just, doesn't always have to be dollar amounts. It could be travel time that you could potentially convert to dollar amounts, or you can come up with some sort of non-dollar impedance measure, like the minutes spent per trip. And you can even have, for the fare, you can add some minutes to the trip. So all you have to do is like come up with like one unit that you're dealing with and go from there. Okay, so you can figure out the demand elasticity. Demand curve's property is that elasticity of demand at a given price. It is the ratio between proportional change in consumption divided by the proportional change in price. So if you take that floor space example, if the price of floor space rises from $40 to from $25, it goes up from $40 to $25. And then the demand of floor space goes from 2,100 square feet to 1,400 square feet. Your elasticity is defined as the change in the quantity of floor space demanded divided by the original floor space demanded. And you divide the whole thing by change in price divided by the original price. So what I want to do is, this example shows you the elasticity value for floor space when the price for floor space changes from 25 to 40, and you get the elasticity value as negative 0.56. Elasticity tends to be negative, right? Because the demand slope is backward sloping, demand curve is backward sloping. So elasticity, typical values of elasticity is going to be negative. But then obviously the magnitude matters as well, like how much negative it is versus not. But typical values are in fact negative because as price goes up, the quantity demanded does go down. What I want to do is, I want to take a few minutes to kind of give you a very simple example so that you can replicate that on your calculators and stuff. So let me go ahead and annotate something here. So my question to you is, if the old situation was the same, but the new situation was actually a drop in price to $20 per square feet, and then the quantity rose to 2,400 square feet, can you use this? Excuse me. Can you use these numbers to get the elasticity value for them? So let's take a few minutes to do it. I'll give you about 3 minutes. Okay. So we're trying to solve this price elasticity value or estimate the price elasticity value, and with these new numbers. And obviously our original situation is still the same. Okay. So I'm trying to work that out here. So it'll be change in the price of floor space divided by original floor space. So change in the price of floor space, I'm sorry, change in the quantity of floor space is plus 300. So I just do 300 divided by the original quantity of, okay, so you do this and then you divide this whole thing. And then you divide this whole thing by the change in price, which is the original price, the change in price delta PS, like it will be 20 minus 25 divided by 25. So 20 minus 25 is obviously negative 5. So I'll just do 5 divided by 25. And then I'll put a negative sign in front of that. So you guys get that? So you could use that. you could use that in calculator. So you 1500 divided by 2100 essentially. So it'll be so to me, this looks like negative 1500 divided by 2100. And if I use that, my calculator, I get negative 7. Is that the answer most of you got? I see some different numbers. If you got a different number, I would love to hear from how you got that, because it's possible that I'm making a mistake. So please, if you are, I would like you to check my work here and make sure that this negative 7.14 is in fact the answer that you're getting as well. Okay, somebody got negative 0.5. Let's think about, could you check your work? So if you got a different number, see which of your numbers differ from what I got going on. Okay, so I see some folks who are affirming. Okay, good. So I see some folks made a mistake realizing that now, which is pretty good. So yeah, please make sure that this is a very important calculation. I mean, in transit companies, this is a very, very important estimate. The elasticity value, knowing the elasticity values is a very important concept and very important thing for them to know. It looks like some folks who had a different number just reported that, yeah, they made a mistake in some calculation. But I hope you're actually checking my number and not just assuming that I'm doing it correctly, because I do tend to make those types of mistakes all the time. Okay. All right, it looks like 0.74, negative 0.74 is the right answer then. Any questions about this? Anybody who still has some questions about it? Please let me know. No questions? Okay, we'll move on to the next slide then. So what I showed you was what we call the arc elasticity. In arc elasticity, we're concerned about a finite change in price that we can measure. Yeah? So essentially, I don't know if I want to do a, so I want to show you the difference between the arc elasticity that I just talked about, but sometimes you can define what we also call the price elasticity. So let me illustrate that with a graph here. So let's say this is my axis, and I'm going to draw two of those. And then let's say this is my demand curve. Let me draw a curvature-based demand curve. So I'm showing you two different demand curves. I mean, let's say they're the same demand curve. So when I talk about the arc elasticity, so I'm talking about, when I say arc elasticity, I'm talking about going from a point here. Let me change the color here. I'm talking about going from a point here on the curve to here. Okay, so do you see the 2 points? And when I say arc elasticity, this is about the price and quantity. Oh, see, it's a terrible mistake because I didn't actually label my axis here. But what I'll do is that, let's say, I don't label my axis. So this is the y-axis is the q-axis, and x-axis is the price axis. So as price goes up, so arc elasticity is based on these 2 points that are sort of far apart from each other, and you're trying to figure out what is the elasticity when you apply the formula that you saw in the previous slide. Okay? But when you're talking about a point elasticity, in point elasticity, you're not worried about that. That's defined over one single point, not over two different points. So if I want to define a price elasticity at this point, so make that point here. And what I'll do is I'll create a tangent at that point on the curve. Okay? I create a tangent on that point of the curve, and then slope of that tangent will be essentially dq over dp. The axis labels are the same, q and p. And then q naught over p naught. Q naught is basically your, this is the price, and so this point is essentially P naught, Q naught. Okay. This point right here is the P naught and Q naught point, and you define based on the I'm sorry, I got disconnected there for a second. I was just trying to illustrate, and I had some nice diagrams here, but let me see if I can recreate those. Okay. So I showed you the idea of arc elasticity before, but let me draw the point elasticity one more time. So this is my axis. Now I'm drawing a curve. And this is the demand curve. So when I'm trying to define a point elasticity, it's over one single point. Okay? And I do it over this point, for example. And to do that, what I do is I draw a line that's tangent at that point of the curve. Okay? And then we know that this point is my P naught and Q naught point. So P naught and Q naught, not P O, but P naught point. P naught. So those points are by P naught and Q naught, and you can define elasticity at a given point then. Okay, any questions about this? I know I got disconnected in the middle there, but I hope you got the discussion in that. So this is what we call point elasticity. That is defined based on the derivative of the demand function at one given point. And for arc elasticity, we need two different price points, so forth. Questions about this? I'll give you a minute here. Yeah, I should have. I didn't miss part of the recording, didn't I? Okay, so I think we talked about the point elasticity, which is defined on the one point on the curve at P naught and Q naught, any given point on the curve, if you take the slope of the tangent to the demand curve. And arc elasticity is defined based on two finite points that you can measure both of those points, and then take the difference based off of that. And then in terms of point elasticity, this becomes dq over dp, which is the derivative of the demand function. And then we talked about the idea of elasticity, very important measure, because it's directly related to revenue. It can tell you whether or not, if you know your elasticity values, you can figure out whether or not you can get away by raising prices on your consumers. Because if you have very elastic demand, then you can't really get away with raising prices on consumers. If you have inelastic demand, which is going to be there no matter what, then you can raise prices on your consumer. And I show you these, business and commute travel elasticity negative 0.5. For leisure travel, the elasticity is negative 1.2. One of the properties of elasticities is that they're remarkably consistent in time. For the longest time, different research papers, they found that for business commute travel, negative 0.5 was a very good estimate of the elasticity for that type of travel. And then negative 1.2 was a good estimate for the leisure travel. Now, however, I think that's my guess. I haven't seen, because we are still trying to find that equilibrium, right? Because COVID is still happening, and we are at a point where some people can still work from home, others have to go back to the office, and companies are deciding what they're going to do. So our economy and our commuting, the whole commuting paradigm as a whole, is trying to find that new equilibrium. But once we do find that new equilibrium, I do wonder if the values that I'm showing you here would hold or not. My thinking is that they might not. They might not hold. So if they may not hold, I want you guys to think about it a little bit. If because of COVID, what we've seen with COVID, a lot of remote work, and maybe it doesn't go back to the remote work level that we had in April of 2020, but if it does settle at a somewhat higher remote work, or at least possibility of remote work, than we had in January of 2020, for example. So if we do settle and find an equilibrium at a higher potential for remote work than we had pre-COVID, what do you think that does to the elasticity for business and commute travel? What happens to the elasticity for business and commute travel? So let me give you some options and ask you what that value might look like. Okay, so I'm going to give you 4 options, and tell me which of these values seem plausible to you. Okay, so I'm going to give you some values. So which of these values, I've given you 4 options here, which of these 4 values look most plausible to you in terms of what would be, in a post-COVID world, what could be the elasticity for business and commute travel? It used to be for remarkably consistent for a long time to be negative 0.05 or negative 0.5. And you could see, you can get some hint from the leisure travel elasticity, which is higher magnitude, still negative, of course, but higher magnitude, higher level. Can you take a guess among what, and you can put it in the chat window for me, which of these 4 values seem the most realistic or most possible value for business commute travel elasticity in a post-COVID world? If we assume that 0.5 is the right value, negative 0.5 is the right value for the pre-COVID world. Okay, so I see 2 responses which are correct. Looking for more. Okay. So we're talking about business and commute travel. Yeah, leisure travel, leisure travel is much more complicated here, because that might fluctuate some as well. But let's think about the business travel, business and commute travel, like everyday trips. So what we're trying to figure out is elasticity of those types of trips. So what would happen if the price of your commute trip rises? Are you going to be more sensitive or less sensitive, or what happens? I see 4 responses so far. I would love a few more. I'll even pause it for a second. So the correct answer to this question is negative 0.8 is the correct answer. And because that represents a more elastic demand than it used to be. You can see, you can get the hint from the leisure travel, right? Leisure travel demand, as I mentioned, is much more elastic because people can forego. If the price rises too much, they'll say, hey, I can't go on this trip right now. People didn't have as many options in commute travel anymore. They didn't before. However, with the possibility of remote work, if your price of your commute rises, I think you'll have more option to ask for flexibility. Maybe you'll spend more trips or more days of working from home. If the transit raises its price or gas becomes prohibitively expensive, if the parking becomes more expensive. So I think people will get a little bit more flexibility in whether or not to take that commute trip that they did not have pre-COVID. And that additional flexibility will make them more price sensitive. Does that make sense? Very important to understand this here. That added flexibility of not actually having to work at the office might make people more sensitive to price. If price rise, they will demand more working from home. They can probably get more working from home. Okay? That's the important idea. And again, I'm not saying that these values are correct. There's going to have to be a lot of research that goes into it once we get to that post-COVID equilibrium. But I think if you had to guess, given what you know right now, I think negative 0.8 would be a good guess. It could be even more flexible. I don't know. I just think among these 4 values, definitely 0.8 is negative 0.8 is the most plausible value. Any questions, comments? Okay, so let's go to the next slide. So demand elasticity has, obviously it's going to be negative because you have downward sloping curve for the most part. And the value also depends on the location of where you're starting in the curve. So the elasticity value is typically not a constant. It stays like at given demand level, it could stay the same. But starting point does matter. Initially, you can get away with raising some prices, but if the prices are already too high, then you might not be able to reach to that point. Regimes of elasticity, it's the idea of whether you have inelastic demand or elastic demand, or you have unit elasticity. Okay, if you have inelastic demand, that means epsilon magnitude is less than 1. That means people are not very sensitive to prices. Even if you raise prices, they will have to undertake that activity or buy that good from you. That's inelastic demand. And that's the realm where you can get away with raising prices. Epsilon greater than 1 is called elastic demand, means there is going to be a much more corresponding to that price change, there will be a bigger drop off in your consumer demand. So you might not be able to get away with price raising. If your epsilon is exactly 1, then you have what we call the unit elasticity. So that means you get a same ratio. So that proportional change in demand is the same as the proportional change in the price. Okay, so that's when you have unit elasticity. Important with regards to the impact of price changes on revenues. So let's look at that derivation. You could do it with the delta thing as well. So revenue that you collect, the initial revenue that you're going to be able to collect, if you're selling Q pieces and charging capital P unit price then times the quantity sold, Unit price times the quantity sold is your revenue. Okay, that's the how much money you're collecting. Now, let's say you change the price a little bit, and now the new price is P plus DP. Okay, and then the new quantity demanded is the new revenue will be P plus DP. And let's just, for the sake of argument, we're just going to assume it's all positive. If any of these values are negative, we can correct that. Okay, so your new revenue would be, if you change the price DP and your new quantity demanded is Q plus DQ. And remember, one of these things would be negative, and that's fine. We're not dealing with the signs just yet, okay? So if you R new will be P times Q. So if you kind of do that first outer inner last, the FOIL method, you know, so that you can simplify this expression, it'll be plus dp times q, qdp plus pdq plus dq times dp. Okay, so this is going to be my new revenue. And if I want to just find the change in revenue, if I want to just find dr, which is the change in revenue, I'll subtract r new minus p times q, right? Because my original revenue was p times q. So if I take my r new, my new revenue, and subtract pq from it, my new revenue would be equal to qdp plus pdq plus this dq times dp, right? Okay, so my change in revenue will be now defined by this expression that I'm highlighting on the slide. A question for you: why doesn't this expression look the same as what I already on the slide? What's the difference between the expression that you see that I just annotated versus the expression that you see on the slide right here? How come the annotation is different than, how come the annotation is different than what you see on the slide here? What's the difference? What do you think is the difference between the revenue expression that I created via my annotation versus what you see here on the slide itself? Yeah, no DQDP term. That's pretty good. You're right. There's no DQDP term there. And I don't have that term. I don't have that term because talking about small change in price and small change in revenue. And when you multiply two small numbers, they're insignificant compared to the first two terms. Right? When you multiply 0.01 to 0.01, for example, that becomes way smaller than any of the original numbers. And that's what's going on here. So differential of revenue, you can just express that in terms of QDP plus PDQ. And then DQ over DP times P over Q. Remember, this is the expression that we talked about, is the elasticity value. This is a definition of point elasticity. This is the definition of point elasticity that I showed you earlier. So based on that, if you sort of rearrange some of the terms with this, dq will be equal to epsilon q dp divided by p. And then you could start to rearrange these things. qdp plus p epsilon q dp over p. So what's happening is that I'm replacing dq. I'm changing this dq expression. I'm changing this dq expression with this one. Okay, so that's all I'm doing. And then based on that, you can derive dr will be this one. And then qdp is the common factor now between both of those terms. And p will cancel out. This p cancels out with each other. So what you end up with is dr over dp. dr over dp is q times 1 plus epsilon. Okay, 1 plus epsilon. Now, epsilon will always be a negative number, remember. Epsilon by itself is always a negative number. What happens if epsilon is less than 1? What happens to your dr over dp? Does it become positive or negative? If epsilon is less than 1, or magnitude of epsilon is less than 1, what happens to your dr over dp? Is it going to be more than 0 or less than 0? I say that here more than 0, right? But does that make sense? Is it in fact correct? So think about this, right? So if epsilon is less than 1, let's take that example of negative 0.5. Negative 0.5. If epsilon is negative 0.5, 1 plus epsilon would be a positive number. Okay. And that means that will make dr over dp to be positive as well. And dr over dp is change in revenue as the price change, right? Change in revenue as the price change. dr over dp is greater than 0 means if price goes up, the revenue will go up as well, because the slope of change in revenue is positive with respect to price. So as price increases, revenue will go up as well under this scenario. Under you have elasticity demand. Now let's think about the leisure travel elasticity value, which used to be negative 1.2. Okay. Leisure travel elasticity value. If this, in this case, elasticity is more than 1, the magnitude is more than 1. So when you do 1 minus 1.2, what happens? 1 minus 1.2, that means 1 minus 1.2 is a negative number because negative 0.2. That means DRD over DP is going to be dr over dp is going to be less than 0. That means what? As your price goes up, your revenue will come down. So in the first scenario, in the inelastic demand scenario, you could raise the price because your revenue will go up, you will collect more money because the people's demand will drop off, but won't drop off as significantly as the price increased. And on the other hand, though, when you have elastic demand, you try to raise the price, demand drops off, and demand drops off proportionately at a higher rate. And in that scenario, as your price increases, your revenue goes down. Is the math clear here? Questions about that? So you can use similar math to estimate the elasticity with data as well. So if you know the two observed data points, if you know two observed data points, Q1, P1 and Q2, P2, you can assume an exponential demand. You can assume the exponential demand function. Let's give that an example. Q equal to K is a constant P raised to power epsilon, which is your elasticity. This is your exponential demand function. Then you could do a log of that function, natural log of ln q equal to ln k plus epsilon ln p1. So then you could estimate your elasticity value for that type of. So if you know that your demand function is exponential, you can estimate the elasticity given the data of the two prices. And in this scenario, epsilon is equal to natural log of q1 minus natural log of q2 divided by natural log of p1 minus natural log of p2. So that's one way of estimating the elasticity. If you know two data points and you also know that the demand function is exponential like that. So this exponent, what I'm trying to tell you is that this exponent of the demand function acts as an elasticity. You can also predict the future data points based on this. You can predict a new data point. You can solve for factor k if you know two data points and you already know your elasticity. You can solve for k. And then you can simply, so once you know k and epsilon both, two equations, two unknown type thing, right? So if you have two data points, you can get two equations and two unknowns in k and epsilon. Find k and epsilon, and then you just plug that value back into the equation. But you can also what we call pivot off the data point, because you know the exponential function is k p3 epsilon gives you q3, right? And then q1. So what you're trying to do is, if the price changes to p3, what will be the given demand? So when you say predicting the new data point, the problem that I'm trying to solve is, what would be the demand if the price changes to p3? If you know that function, so predicting the data points means what would be the demand if the price changes to p3? So what you can do is you can pivot off the new data point, q3 equal to k3, or I'm sorry, k, which is a constant p3 raised to power epsilon, q1 equal to k p1 raised to power epsilon, based on the exponential demand function. You do the ratio, p3 over p1 raised to power epsilon, and you know both p3 and p1, and you know the original quantity demanded. In that scenario, you can get your q3 values. The quantity demanded at price 3. Questions? Okay, so we can also do similar ideas with cross elasticity. So you can figure out, not just remember how we say the cross elasticity of demand. We can, if the product we're talking about is not the same, so we go back to our yard space, floor space example. So if you're trying to figure out the elasticity of floor space quantity with respect to the price of yard space, then that could be positive. Cross elasticity, it's the ratio between the price change of a good and the proportional change of consumption of an interdependent good. An interdependent good in this case was the floor space as the price of yard space changed. From $10, from $5 to $10. What would that do to the demand of floor space? It might increase it, and that's why the cross elasticity could be positive. Income elasticity is another related concept where proportional change in consumption and proportional change in income. So how much more would you consume if your income rises a certain level? That's what we're trying to do here. If your income rises by a certain level, what is your proportional change in consumption? There are some other demand model forms. You could have a linear demand function with a negative slope, and then you could define epsilon using, so if you had a linear demand function, Q will be equal to A plus B times P, where A and B are constant. And if you solve for epsilon, you can figure out what the epsilon is going to be, because remember, the definition of epsilon is right here. dq over dp, p naught over q naught. So if you know at any given price point, you could figure out so let me try to see if I can show you how that formula comes to be. So remember, epsilon, which is the elasticity, it's equal to dq over dp, okay, times q over p. Okay. Oh, I'm sorry. Is it p over q or q over p? No, it's p over q. I'm sorry. Okay. So it's p over q. So epsilon is the elasticity times dq over dp. But if it's a linear expression, we know what dq over dp is going to be, right? For a linear expression, what's going to be the slope of the line? What's going to be the slope of line in this equation? Q equal to A plus BP line. What is the slope? Okay. So the slope value, dq over dp for a line is B. So I substituted B because line is of the form Q equal to A plus BP. So then that becomes B is the slope, and B times P over Q. But this expression doesn't quite look the same as what I have on the slide. But you can make it look the same, right? How would you do that? So thank you for your response. All I need to do is, I just need to substitute for Q, because that is same as B times P divided by A plus BP. That's it. Okay, so and then you can do the same thing that I showed you in the simple exponential. We remember we said A Q equal to A B P raised to power B, and we said that epsilon is essentially the exponent that you're using on the price in the case of simple exponential functions. You could also have multivariate exponential functions. Q equal to A times P raised to power alpha, P raised to power beta. So you could have a sensitivity to the price, but you could also have a sensitivity to the travel time. So it could be multivariate exponential functions as well. So alpha would be called the elasticity with respect to the price, and then beta will be called the elasticity with respect to the travel time. Elasticities are transferable. You can think of these as sort of an initial rule of thumb. So these are sort of good models to use when you're trying to solve some problems. And you'll see some examples of that in your homework. You can aggregate the demand, because obviously demand decisions, quantity demanded and price and all these decisions are basically made by, they're basically made by different folks, right? It's basically they're made by individuals in the population. So you can sort of add up individuals' travel preferences or demand preferences to get what we call a population demand curve by adding up the individual demand curves. So that's what's happening here. You have individuals have AI plus BI raised to power P, or not BI raised to power, AI plus BP, BIP. And then when you're trying to figure out the population demand, you just add all the expressions, the summation of AI plus summation of BI over multiple individuals. Obviously, if it were a non-linear demand function, then mathematically it's going to be much more complex, and I'm not going to get into all of that. The concept is simply to add the individual's key value for given values of price. So you basically just take individuals quantity demanded at any given price and just add them up for everybody in the population. Right? Questions? Okay. Now we have to think about the transportation supply curve. In fact, I should probably stop here because I want to. So I'm not going to be assigning any new homework or anything like that. I will just stop here because I want to have this discussion, the supply curve discussion, because there's some important concepts that we need to cover. So I would like to have a full lecture for that. So any questions about this? Okay, no further questions. I'm going to stop the recording here.